So good morning. It's a pleasure to introduce Professor Prabhakar Pathak to all of you. I'm really happy that he accepted our request and agreed to deliver a talk at the Ansys premises. So Professor Pathak received his PhD from Ohio State University in Department of ECE, where he later joined as a faculty and became a professor. Currently, he is a professor emeritus at Ohio, and he served as an adjunct professor at University of South Florida. He is regarded as the core developer of the Uniform Geometrical Theory of Diffraction (UTD), and his interests are in the development of ray, wave, and beam optical methods in frequency and time domains for solving electrically large electromagnetic antenna and scattering problems for engineering interest. He has developed a lot of hybrid methods which combine the best features of any of the above methods with the numerical techniques to solve the EM problems, which cannot otherwise be solved in a tractable fashion by any of the methods when used alone. So his work is applicable to like prediction of EM radiation, coupling associated with smaller antennas, larger phase array antennas placed on the near large structures like airborne, spaceborne structures, as well as to the EM scattering by such structures. He has presented many invited lectures, short courses in US and abroad, and also he has published 7 book chapters and recently published a book which is like a Bible of the electromagnetics entitled Electromagnetic Radiation, Scattering and Diffraction, which is co-authored by Professor Burkholder. Now he was an associate editor for the IEEE transactions on antennas and propagation. He was a distinguished lecturer at IEEE, and he was the chair of the IEEE AP Distinguished Lecture Program, member of APS AdCom, and he received numerous awards like AP Shelnoff Best Paper Award, George Sinclair Award from Ohio State University, ISEP Best Paper Awards, Millennium Medal, and other as well. So I'm happy to have him here, and I request Professor Pathak to take over the stage and go ahead with his lecture. Over to you, sir.
So, ready to start now?
Yeah. Just one update, sir. Not only I'm being presented, so many people from academia. And
So, they can probably see me. I don't know.
yeah, they will be able to.
They can see the back of my head. And so, good morning, and thank you, Ashutosh and Nijas, for organizing this get together here. It's an honor to be here. Actually, I have some tenuous connections to Ansys because one of my very good friends and colleagues, Professor Jinfa Lee, who worked at Ohio State University, actually did some of the first coding that went into what became HFSS later. His advisor, Professor Cangelaris, I think, started this whole thing along with Jinfa Lee. And then Jinfa Lee, of course, came to Ohio State, and he was at Boston University, came to Ohio State, and then he started his career over there. But anyway, I think he's, in my opinion, one of the best professionals in the area of numerical methods in electromagnetics, you know. So, but he's just retired, by the way, recently. So, okay. So coming back to this talk. The title is A Brief History of Ray Methods from Ancient to Modern Times and Their Impact on Electromagnetic Engineering Applications. And the short history of this historical talk is that I was asked to do this 2 years ago at the UCAP meeting in Florence. UCAP is the European Conference on Antennas and Propagation, which is like the analog of IEEE Antennas and Propagation Society, you know. So, but it's the European one, and they wanted to talk about the history of electromagnetics. There were some 5 lectures, and they asked me to talk about the history of ray methods. And I presented this recently to a bunch of students. There was a conference. There was a conference in Hyderabad, mostly for students, and I thought this would be a good topic for students to get interested in ray optics. And I'll give you the reasons why ray optics excites me so much and has a great potential for a lot of things. You know, I'll be talking about that. But I had oriented this more towards students. But here you guys are all professionals, well equipped with advanced numerical methods and all of that, which HFSS Ansys uses. So I don't know if this would be too historical for you, not enough meat. But if you want to, I can discuss things afterwards about this. But what I'm doing here is basically coming to the modern applications of electromagnetics, modern applications, and the question is, how did we arrive to this point? So I thought it'd be fun to trace it through the history, because I was asked to do that, and since I did I'm not a historian, for so I'm old enough to be a historian, but I'm not a historian. but you know, I did put in some time to figure out how people develop these methods, and so I put together. So I thought it would be nice to sort of talk about that, and for students, you know. But anyway, I'll make it more interesting for professionals. But even after the talk, if you want to talk, we're going to have some kind of a discussion group.
Definitely.
I think we can talk some more about the nitty gritty of things, which I probably won't do here. This is going to be a very popular lecture, but I guess is everybody here conversant with numerical or computational electromagnetics? You are familiar with the techniques.
Yes.
Right. Okay. So, but I'll try to point out why array methods can complement what you already know. Okay. So with that introduction, let me start. My hope it's not going to be too elementary for you. Oops. That looks nice too. But anyway. Okay. So let's. Here are some other sources. Do you have a copy of this thing by any chance? But this is recorded, right?
This is recorded.
So you can follow this. This is where I got a lot of things from. For the information I got for these slides. I want to make one little advertisement stop here. Some of the figures I've taken from a recent book that I published with Burkholder, who's actually my former student, and he's himself a professor, not Professor Emeritus, he retired too. And actually, he was the advisor for Nikhil Grover that is sitting over there. So, but anyway, Bob was my best student at that time, and I asked him to write part of the book with me. So there are 18 chapters. Anybody that's interested in array methods or wants to know more about it and wants to know about really electromagnetics as such, you know, the basic ideas, the physics behind Maxwell's equation, there's so many other things. It's got a lot of good information you won't find in any one book. So I put a lot of time into it. 7 years, not continuously, but you know, from time to time. And I made it so that people would be able to see why we do certain things the way we do them in developing electromagnetics at the graduate level. And you can start with an undergraduate background and ramp up very quickly to graduate level. And it's also good for professional engineers if you want to go back and review stuff or get to some topics that are somewhat new. I think in it.
That book is with me, so you can have a look if anybody
You
wants.
didn't bring the book with you, but
Yeah,
it's on
it's too heavy.
and hopefully it'll be reviewed very soon. It came out 2 years ago, but it didn't get good publicity because the publisher didn't do anything about it. So basically, it'll be reviewed very soon, and hopefully it'll be published in the AP magazine, and then more people will know about it. But I think it's a nice book to have, actually.
So
So it covers a lot of things. And there are 3 chapters that are written by Burkholder. I asked him to do it because he's far better than I am at numerical methods. And he talks about integral equations, fast multi-level FMM, and so on and so forth. And he also talks about characteristic modes. And then he and I worked, actually, part of his dissertation was on the topic of beam. So I write that too. So, and the rest of the 15 chapters have been taken from most of my lectures and add-ons. That I added a lot of things I didn't lecture on before, but they're in there. Those topics are. I think you'll enjoy it. So, you know, look at it. So with that, let me go ahead and.
Yeah. Now, yeah.
There we go. Okay. All right, so without too much, an hour, can I go over like 10, 15 minutes or anything? Is there a problem with?
No problem.
No problem.
Okay. So, okay, why do we want to emphasize ray methods here? Because, um, the ray methods offer you something that no other method offers you, and that is physical insight into radiation and scattering mechanisms, electromagnetic radiation and scattering. Okay. It provides a very vivid picture for radiation and scattering in terms of rays. So the engineer can see where the scattering is coming from or where the radiation is coming from. And this is very useful if you want to do design, like you want to control the scattering, radar cross section, whatever you might be doing, or if you want to control the radiation pattern and so on. So you need to know the interaction between the antenna and the structure, the platform interactions, and the ray methods give you a very nice picture for them, which you don't get in numerical methods. What happens in numerical methods is you get a lot of numbers, right? You're crunching numbers. And let's say you want to do an antenna on an aircraft at X-band. It'll take you many days to compute the pattern. And then what you get is a bunch of numbers. It won't tell you what's causing this or what's causing that as an engineer. So if you have this background, you can tie that information with this. I'm not saying numerical methods are no good. Absolutely not true. Numerical methods are very essential, and they do provide. They're known as full wave solvers or whatever in your software, and they take into account all the electromagnetic interactions in a self-consistent way. And that's why they become cumbersome and numerically inefficient as the radiating object becomes electrically large. By electrically large, I mean large in terms of the electrical wavelength. Now, if the wavelength becomes short or the frequencies become high, then the number of unknowns that you solve using numerical methods goes up exponentially and it becomes a problem, right? And so therefore, at that time, if there are enough available solutions in the ray methods, then you use the ray methods to give you your answers. And we'll show you what can be done with ray methods today and what are some of the things you can do to improve it or expanding the range of problems you can solve by the ray methods. Okay. We already can do a lot, by the way, but there's always more to be done. And so that's the most important thing is the power and the simplicity of the ray methods. You don't get it in any other methods. So that's the important thing. Now the ray methods obviously provide you with an analytical solution. That's why you can see analytical solution is like some sort of a mathematical expression which is derived, and then it can tell you like if you change these parameters, that's how the solution will change. So that's very nice. And again, it provides analytical solutions to problems you cannot solve exactly in an analytical fashion otherwise. Like you can do only a few electromagnetically separable problems exactly, right? And can do everything exactly, except you can write an analytical equation for it or something in a general problem, but then you have to solve it numerically, right? So analytically, there are very few problems you can do. And ray methods can allow you to solve a larger class of problems analytically, but they're approximate. But they're very accurate in terms of moderate to high frequencies for application. So if you are working with, okay, let me digress here. I can make a bold statement saying that if you're studying scattering problems, I've been able to show that I can bring this method down almost to the resonance region and very accurately. But then you have to include some multiple ray interactions, to make that happen. But usually you don't need more than a couple of interactions at the most. And it's good for moderate to high frequencies. Numerical methods are good for moderate to low frequencies. So there is a gap in between, but you can fill that with a hybrid technique. So we also work on hybrid methods where we combine the best features of both methods. A lot of practical problems involve large structures on which are mounted antennas, which is not necessarily small, but the like array can be a large one, but the elements, the antenna elements of the array can be electrically small, right? Yeah. So then you have to worry about how do I mix the two? And we've solved that problem recently. That's another topic, but anyway. So that's one thing that can be done is to hybridize. And then finally, I want to point out that
Yes, now you stop it.
I'd go to the point is to where did all this start? You know, obviously we came to the Ray methods, but where did it all begin? So I hope I don't bore you, but I'll go very fast through the old history. Okay, we started in the 700 BC time frame, and what people started to do then was they took crystals, quartz and other kind of crystals, and they polished them, so they became very transparent. And then they saw lens-like properties happening, you know, so they tried to play around with that for a long time. And nothing much happened until they started to make glass, and then they make glass lenses and so on. Then a lot of things started to happen, you know. But till then, at least they started with these crystals and polished them, and then they saw some of these. And then in the old days, people were not only interested in making lenses and so on, but they were also interested the so-called scientists of those days. You know, they were also interested in explaining vision. How did we see things? You know, and you'd be surprised at the ridiculous kind of explanation they came up for vision. We laugh at it now, but at that time you can imagine. You know, it must have been hard to figure out when you're starting to first see what causes vision. But anyway, I won't go into that. But a lot of these scientists not only worked on studying light and how it goes through lenses and so on, but they also try to explain vision. I'll go directly to this 5th century now. The people that made some impact among these 4 people, I think I'd like to mention Euclid, 300 BC, and Hero. He got us into the AD, you know, after Christ, before Christ and after. What was Euclid? Euclid was they call it geometer. I didn't know that a person that does geometry is called a geometer. Okay, I learned at that time when I was making this. He was a geometer. And so what it means is that he came up with this geometry for flat spaces, right? That was Euclidean geometry, if you remember. And then, of course, it wasn't complete. So it was extended later on to curved spaces by Riemann. So that became Riemannian geometry later on. Okay, but anyhow, Euclid sort of proposed that the light came to the eye from objects along straight lines. So now the notion of rays is beginning to take place slowly, you know, straight lines, okay? And then, of course, Hero said that light also travels in straight lines, but at infinite speed. Those days, they thought light was almost instant, right? Or it was instant. And so instant means traveling at infinite speed. So they're starting to look at this more scientifically, slowly. In AD 1000, there was an Egyptian guy. Well, actually, he was originally from Syria, and then he moved to Egypt. But a lot of people regard him as the first scientist, you know, official scientist, because he said that if you make any hypothesis, you must prove it experimentally or mathematically. Otherwise, it doesn't hold water. You can't just make a statement and say, this is it, you know. So he started some kind of a systematic way to study things. And that's why he's called the father of modern science, actually, or science, I should say. and he's also regarded as the father of optics. Now, although he was born in not Syria, pardon me, Iraq, he came to Egypt and he formed like a center of optics over there. And you wouldn't believe it, but people from all over the world came and studied in Egypt at that time. Romans came, Greeks came, so many other people came. So there's Al-Hazim. And he is the one that came up with, if you studied undergraduate physics, you probably studied pinhole camera. You make a box with a little hole, and you have a candle. You can see on the backside, if you have a thin paper or something, you can see the candle upside down. You know? Okay, so he's the one that came up with that. And he also did something very important. He said speed of light is finite. The first time the guy came up with something like that, you know. Don't know how he came up with it, but he said that light it travels at finite speeds. So, by the way, is this becoming like sort of a interesting topic, or should I go quickly to the?
No, this is interesting.
Okay, so also I'm talking loud enough, like everybody can hear me.
Yeah, I think. Yeah.
So, then what happened was in 1600s. Now he started in 1000 AD, but coming up with his ideas. But he superseded by Snellius. And Snellius gave the laws of reflection and refraction. So now you're beginning to see a little bit more scientific stuff coming out. So if you had an interface between two media, everybody knows you come in with an incident ray, you can reflect such that the angle of incidence, which is the angle made by the incident ray with the normal to the surface, makes the same angle as the reflected ray makes with the normal. And then if you go into the other medium, then there's a relationship between the transmission angle, which is the angle between the transmitted ray and the normal, and it's related to the incident ray through some parameters of the medium. And those were the laws of reflection and refraction. So these are Snell's laws. Snellius became Snell.
But Alhazen didn't know this, right? Refraction.
Say that.
Alhazen didn't know about the refraction, right? This.
Al-Hazan.
Al-Hazan didn't know about. Oh, Al-Hazim.
Yeah.
No, he knew, but maybe not the laws. But he knew, obviously, he knew that he was refracting things and he was like bouncing things off things. But there was no law that said, you know, the angle of incidence and angle of reflection are the same. Snell had to come and show that, experimentally show that. But you remember, you'll see as we go along, Snell's laws were rediscovered again and again by different people with more and more sophisticated mathematics, you know. Okay. The person that contributed most to ray optics in those days was Descartes. And he was also a mathematician. And today, the geometrical optics that we know was mostly based on his foundations that he laid. And Descartes did a lot of contributions. And of course, one of the more important things he did was to, he provided the correct geometrical optics ray, well, besides giving the ray concept. So he established geometrical optics was a ray theory. Okay, so he established that. And then he gave a ray picture for the formation of the rainbow. And how does that work? Well, according to him, when the sun is behind you and there are a lot of rain clouds or moisture in the clouds, a lot of moisture in the clouds, water vapor, then the water droplets, I'm just making them spherical, okay, but they're not necessarily spherical. They may be spheroidal, but for all practical purposes, they're almost spherical. And what happened was that the ray would hit from the sun into these droplets. And since the sun had a rich spectrum, it was white light, it had a lot of frequencies of light in there. As we know, now the 7 colors of the rainbow, when you sort of mesh them, if you have a wheel with the 7 colors and you spin it fast, it'll look white. Okay, so white light gives rise to different spectra as we know it. and the different frequencies of light would then refract along different angles, and they would then undergo what's known as total internal reflection. There was no refraction. Uh, but then you say, where did the energy go? Well, not only just in the reflected ray, but there was also an evanescent field, which we know now, but we don't talk about it here. Okay. But basically, you have a total internal reflection, and there gives you this red will refract in a certain direction, and the blues will refract in other directions. So you might have another ray that goes like refracts in a different direction from the red, and then it refracts more towards the normal. It doesn't bend as much. Okay. So it bends more towards normal. Okay. And then it would go through a total internal reflection and then give you the blue here. And this would be coming, so all the red rays would come like this in a parallel fashion. All the blues would go like that. And that would give rise to the different bands that you see. And if you move now, this had to be, the sun had to be behind you, but there's no room here. So, but remember, the eye had to be here somewhere. The sun is behind you. So that's what happened.
So, like the evanescent mode is completely ignored in ray optics, right?
In those days, yeah.
Okay.
But we know there is a field. The boundary conditions dictate that there's something on the other side also, right? Unless it's a impenetrable surface on the other side, then or conducting or something, totally reflecting surface.
Yeah.
But that wasn't that important. Most of the energy is in the total interaction. Kepler did something, but I'm not worried too much about him right now. He went to curved, like people were dealing with flat surface. He did something on curved, but he's doing that for creating mirrors and lenses to study what you call the planets and stuff. So, and the motion of them. So you know Kepler's laws. He was a mechanics expert in mechanics. So, all right. Then comes Fermat in 1600. He used the principle of least action. That's known in our variational calculus, right? Like the optical path length is an extremum, so it can be a maximum or a minimum. Generally a minimum, but there are places where I can give you examples where you have both shortest path, longest path. There are situations. So it's an extremal path, and based on that, you can show Snell's laws. So you can derive Snell's laws from saying that the line joining the source to the observer with a constraint that a point on that path lie on the reflecting surface, okay, is an extremal. When you do that, you come up with the law of reflection.
But so it was not formulated with this Lagrangian and all.
It is related to that, but this guy was a mathematician also, but it's related to Lagrange's equations. But you know, it's basically a variational method. So Lagrangian, you know, talks about the variational properties. But you can talk about optical path length as being the thing you want to optimize, or you want to basically find out its maximum limit. So you do that, you come up with Snell's laws. And so far, everything is rays. You know, light travels along ray paths so far. And then finally, there was this guy after Fermat. Fermat was the one that came up with the Fermat's principle. There was a guy that was in Italy by the name of Grimaldi. Okay, Fermat was a French guy, and Grimaldi came up in the 1618s to 63, and he started to see bending of light. So if the light went through a hole, he said, on the other side, you see a spreading. It's not just going in straight lines. You know, what happened here? So is light really traveling in straight lines? Ray is a ray solution, the correct description for propagation of light. And the way he found this was very interesting, you know, not only through a hole, but one day he was observing through a keyhole in a door, and he saw light and dark rings. What was happening is, now we know, is that light was diffracting, and the diffraction from various points on the edge of the keyhole were causing interference. They came in phase, out of phase, in phase, out of phase. So you saw bright and light rings, Now, if you ask me, what was he doing, trying to look through a keyhole? What was he looking at? I don't know. That's anybody's guess. But he was able to show something that hadn't been observed or questioned before. So people began to think, what caused this? So they started to think of maybe the light acting as a wave of light, not just a ray of light. Now the notion of waves is starting to come. The question is, what is light? Is it rays or is it waves? And that exists even today, right? With photons. Sometimes they behave like waves, sometimes they behave like particles, quantum particles. Light quantum. Okay. Photons. So, okay. So we come to Huygens. Huygens says that light is a disturbance. It's like there's a wave, And he explained that if you take a wavefront, then you can have every point on that wavefront becomes like a secondary source. So the spherical waves that are generated from every point on that wavefront. And then that, at a given time, say this wavefront is formed at some time t equal to t0. Then sometime later, you have all these little spherical wavelets that form another envelope. And that then describes the subsequent wavefront at a later time. And this can be carried further and further. So that's how the wavefront expands and the light travels. So according to him, this is how the waves worked, and it was a wave theory of light. And this could explain bending, because you can go in all directions from the spherical wavelets are going all over the place, right? From the wavefront. Okay.
So before this, there was no concept of superposition of fields and all. No.
The length. And Newton came up with a particle theory of light. So he was thinking about particles, So there's a ray theory of light and a wave theory of light, and then there's a particle theory of light. So as we know now, quantum mechanics talks about photons, but at that time, Newton's particle theory fell apart. It couldn't explain the bending of light. Particles went through bending. So, but Newton, of course, did so many other things, right? So we know gravitation, calculus came from Newton.
But with the particle theory and principle of least action, still we cannot get that.
No, there is a good point. There is people like Markowitz, I don't know if you know, but they're connecting particles to the variational principle, like a Lagrange or something.
Okay.
And they're trying to think of it as photons, but I don't think it went everywhere, but anywhere. But he started to look at it from that point of view. Actually, it's not too old an article. Anybody here heard of Markowitz?
Yeah, Markowitz, yeah.
Huh? Yeah. I'm glad somebody heard of him. But Markowitz
waveguide theory. That guy gave the waveguides concept.
Yeah, right. Markowitz.
Yeah.
And his student was Felsen, by the way.
Yes.
I met both of them, by the way. I knew Felsen very well. We knew each other quite well. But Markowitz, a very nice man. I mean, you would think that such a big guy would have, would not be so easy to talk to, but he was very, very friendly guy. Very nice person. So anyway, the reason I'm mentioning it is he tried to talk about electromagnetic waves as particles. So there's an article in the proceedings you might be interested in. He tried to basically use quantum ideas and I don't think it went anywhere. So, but it's an interesting thing. All right. Someone about to 1800s and beyond. By the way, does anybody else know who else discovered calculus besides Newton?
Lagrange or
It was Leibniz.
Leibniz, yeah.
Okay. Yeah. And I know that because my professor of calculus in Mumbai, where I studied, he told a story which was interesting. He was always full of stories. So he told me that's the first time when they met each other for the first time. That's the longest that people of the same sexes have looked at each other ever, because they were enamored by how could he come up with the same thing I came up with. So they looked at each other, but they were both men, they're looking at. So normally he used to make all these funny stories about, boys and girls. So, but this was man to man, looking at each other forever. So anyway, because they're so enamored by seeing another person came up with the same idea. Okay, so let me go to Sir Thomas Young in 1800s. He wanted to prove that light was definitely wave theory. There was a wave theory of light, not ray theory. What he did was took a screen, took two holes in the screen, had a candle, and then he showed through his picture here that you have these Huygens waves, and what they do is they come and interfere with each other, just like water waves. You throw a rock in a lake or something, which is calm. It creates ripples, right? And that's because with the troughs and crests, so crests are where there is constructive interference, troughs are where there's destructive interference. That's exactly what you see here. Let me try to show you a quick picture, by the way. This is what he presented at the Royal Society in 1803. This was his hand-drawn picture of how the interference took place from the two slits, A and B. So this may look elementary to you now, but at that time, people were trying to figure out what's going on. So let me go to this.
So those are static,
Sorry?
standing wave patterns, mostly, right? Kind of a standing wave pattern.
Yeah, standing waves. Yes, exactly. Precisely. So, okay. So, Thomas Young, he was actually a very interesting guy. He was actually a medical doctor. In the, I think the Queen was the reigning ruler at that time of England, and he was a physician to the royal family. But he also knew many languages, and he was also a scientist. He did a lot of work in science. And so he tried to explain diffraction by using the wave theory. But then he said, something tells me that light also maybe bends and goes in different directions along paths, ray paths. So let me try to write a ray theory of diffraction. So he said there are two rays that start from the middle of each of these holes, and they go like in the far field, they're going parallel. And some directions they add in phase, some in out of phase, and so on and so forth. So that would also explain the maximum and minimum. He did that, and actually it did coincide with fairly well with the maximum minimum. But the problem he had was the amplitudes were not big. And that's because he didn't know how much diffracted in this direction versus that direction. So he, at that point in time, he couldn't predict that. So it was a good attempt, but at that point, it didn't work as well as another theory that came, which was the wave theory by Fresnel. Here's Fresnel, another French person. And so he introduced a more accurate, based on Huygens principle, and that agreed much better in terms of amplitudes and also maximum minimum. It wasn't perfect, but it was much better than what. So at that point, they threw out the ray theory of diffraction. So they said diffraction was something other than geometrical optics. Bending caused diffraction. Bending of rays. So people said, okay, light is waves now. Okay. Later Maxwell came, And before that, there was an experiment by Michelson-Morley, if you know, which said the speed of light is independent of the motion of the source. What is it dependent? Depends only on the parameters of the medium, mu and epsilon, as we know today. Uh, that's all it depends on. It doesn't. The speed of light doesn't depend on anything else. It does not depend on the motion of the source. That means source is moving. I don't care if I'm coming close to the source, going far away from the source. I always measure the same speed of light, and it was a universal constant, equal to 3 times 10 to the 8 meters per second. That was in free space, okay, in free space. But the speed would change in the medium. So if for a different medium, you get a different speed, but it'd be constant. Okay. So Maxwell then in 1800s came up with the famous Maxwell equations, and everybody knows about that. It's going to that. And what he interestingly pointed out was that, well, first of all, he predicted the existence of electromagnetic waves through just his equations. He went to the wave equation from Maxwell's equations, and he showed that electromagnetic waves were produced, okay, by changing time-varying electric field would produce a time-varying magnetic field, produce a time-varying electric field, and so on and so forth. And you'd get wave propagation. And then this was later on proved by Jagdish Chandra Bose, and it was proved by Marconi. Well, yeah, Hertz actually, and then Marconi showed that you could use radio waves to communicate over longer distances. So all that happened afterwards. But Maxwell, through his equations, this was one of the few times theory has shown something, predicted something that was then later proved by experiments. And that is also true of Einstein's theory. But more than that, I want to say something here before I go on, that he found out also that electromagnetic waves reflected and refracted with the same laws that light did, Snell's laws. And he found that electromagnetic waves behaved the same way with materials as optical waves, light waves. And he concluded with all these things that the speed of light was the same as the speed of the electromagnetic wave, by the way. He came up with the speed of electromagnetic waves to be the same as the speed of light. So he said light and electromagnetics are the same thing, okay? They're not different. So he's the first one to unify the two. And about that time, Einstein, of course, later came with his very, very famous special theory of relativity based on a couple of things. Constancy of the speed of light. In relativity, special theory of relativity, the speed of light is a universal constant. Whereas in Newton's theory, what is constant? Time is a universal. Like it's the same for all frames of references, whether they're moving relative to each other or not, doesn't make any difference. They all see the same time, according to Newton's laws, which Einstein proved wasn't the case. And because he used the constancy of the speed of light. And he used the so-called Lorentz transformations, if you know. Everybody knows, right? You've seen it. And where did Lorentz transformations come from originally? Lorentz got it actually from Maxwell's equations, I think. They had to do, that's my opinion anyway. But I think he got them from Maxwell's equations. Maxwell's equations automatically satisfy Lorentz transformations, which means it's consistent with relativity. On the other hand, Newton's laws do not. Yeah.
Fitzgerald contraction and all those things.
Yeah, all that thing was part of the Michelson-Morley thing. And then Fitzgerald here, they were looking at stars and they were looking at aberration of stars, right? That was what came up with what you're mentioning. But basically, it's all tied into the same thing. But okay, Lorentz transformation. So look at how important Maxwell's equations are. It tells you, electromagnetic waves exist and they travel at the speed of light. Optics and EM is the same thing. It satisfies Lorentz transformations. So we didn't have to change with Einstein's theory of relativity. Maxwell's equations didn't change. They stayed the same. Beautiful. But Newton's laws did not satisfy Lorentz transformations. So his theory had to be changed, not Maxwell. There was some question about whose theory was going to be changed. And it turned out that Maxwell's equations, they seem to be holding up in every situation. We use them at microscopic scales, but in microscopic scales also you can use Maxwell's equations along with some other things you have to include in them. And I'm not an expert in that, but quantum electrodynamics does build up on Maxwell's equations actually.
So the vector potential has some meaning in quantum mechanics.
Say that, yeah, quantum.
Vector potential has some meaning in quantum mechanics.
Yeah. In fact, they quantize Maxwell's equations in cavities and show the connection between those quantized modes and the quantization of wave functions, in potential wells and stuff like that, the same eigenfunctions, eigenvalues and stuff like that. Yeah. And then quantum electrodynamics, where relativistic quantum electrodynamics, not just that they bring in relativity also inside, but then it gets complicated. I'm not into that, but someday maybe I'll have time to study it, but I don't know enough about it, so I won't say too much. And Kirchhoff used Maxwell's equations in the late 1800s. Now see, things are getting more mathematical. They're trying to justify based on wave theory what's going on. They're trying to explain optical phenomena or electromagnetic phenomena by now, if you want to call it, because electromagnetics and optics are the same. And he studied the diffraction by an aperture in the screen, Kirchhoff approximation. Everybody familiar with Kirchhoff? Yeah. So what you do is you take an aperture in a screen, you send a wave onto the aperture, find out what's on the other side of the aperture. So you use initially the incident electric and magnetic fields as a starting point and use that as an approximation to figure out the fields radiated from that. Now use Maxwell's equation to come up with a radiation integral that integrated over the aperture. And he came up with the light and dark things, and a main beam on the other side. So he was the first guy to come up with some mathematical expression that made more sense than Fresnel's original wave explanation of diffraction as compared to Thomas Young's failed ray theory of diffraction. But also remember, Young showed that through the double slit experiment that light was waves. But then something bothered him and he said, I can maybe do this with rays also. So there was something like that was going on. To jump ahead, there's a connection between rays and waves. And it turns out that wavefronts and rays form a normal congruence, they call it in differential geometry. So if you have a surface, the normal to the surface corresponds to the rays. Normal to the wavefronts is rays. And the rays will travel least, they travel extremal paths, which mean they're geodesics. In an inhomogeneous medium, they bend, but in a homogeneous isotropic medium, they're straight lines. And so geodesics become straight lines. So remember, all ray paths will travel along geodesics. That's number one. And that's useful for Ansys because I'm coming to something that maybe you guys will be interested in incorporating into Ansys.
Kirchhoff was the first one who derived that at the focal plane it's the Fourier transform of.
Who did?
Kirchhoff? No.
Kirchhoff. Yeah. But the focusing, you're saying?
Yeah, at the focal point, the field will be the spatial Fourier transform, right?
Oh, not necessarily. No, it's only the far field that the Fourier transform of the aperture field is the far field. The relationship. But that's only on a flat surface.
Mm-hmm.
But of course, if it's not a flat surface, if some radiating surface that is weird, you can always project that on a flat surface and then use equivalence theorem and then go. Then the relationship between the far field on that infinite plane is the same thing as the Fourier transform of that distribution on that plane, right? That's cool. Okay, but anyway, let's go from Kirchhoff is the first guy that started to look at it from a mathematical point of view. He took Maxwell's equations, integrated that on the aperture, and came up with his integration was like summing on the wavelets in the aperture. That's the integration. Okay. But he came up with that. And then came up Sommerfeld. Now we start to get to the more interesting part of computational electromagnetics. Okay, he came up and he started to talk about diffraction from a half plane. And he took a perfectly conducting half plane and he excited that with the so-called plane wave, because now at that time Maxwell's equations could show in rectangular coordinates that the solution to the wave equation is a plane wave in rectangular coordinates. You can show that. And so he took a plane wave and hit the half plane with it. And he was able to, as a excellent mathematician, applied mathematician, he showed that there was a closed form solution to this problem. Excuse me, which today we can solve by the Wiener-Hoff method. But he didn't solve it by the Wiener-Hoff method, he solved it by another method. Okay, so he came up with an explanation. He showed that the field at any point was given by the incident plane wave and a reflected plane wave. And there was a contribution that came from the edge, which was like a cylindrical wave that went to the observer.
Additional edge diffraction.
That is diffraction, right? So the first time, mathematically, he showed, based on wave theory, that diffraction, there's a diffracted wave that comes from the discontinuity, the edge, the edge. So he quantified it, right? And now mathematics is taking a hold and trying to explain the physics here. So mathematics and physics are working together. That's the nice thing about electromagnetics. By the way, I got inspired into EM because my original background was physics, undergraduate in India, and mathematics was my minor. But then I found that electromagnetics was one place where the physics and mathematics tied together and really explain phenomena. And the person that got me to thinking this way was a professor of mine, and whose name is Chalmers Butler. By the way, he passed away 2 days ago, but anyhow, so he was the one that inspired me into, and he was one of the best teachers, could tie mathematics, complicated mathematics with the physics, That was the beautiful part. Just mathematics by its own sake is beautiful, but as an engineer, I'd like to see it used, and as computationally young people, I'm sure you feel the same way. It's nice to see it being used somewhere in a practical way. So, okay. So Sommerfeld was the first one. Then came Pauli. Pauli did the same thing that Sommerfeld did, but to the wedge. If the wedge is a more general case, flat faces, but if the wedge now collapses to a half plane, then you get Sommerfeld solution.
Mm-hmm.
Now the problem is Sommerfeld wrote his solution as an integral, which he could do exactly in terms of Fresnel functions. So he showed that diffraction could be described in terms of Fresnel integrals. So one thing you'll notice as I go along is that there are special functions that are characteristic of every diffraction process. In the case of edge diffraction, it's the Fresnel integral. Okay, so he came up with that. Now there was a guy called McDonald who came up with an integral expression for this problem here, plane wave diffraction by a wedge. And then Pauli took that expression, which was an integral form, and evaluated that asymptotically for high frequencies. So now he approximated the integral asymptotically, and you may have heard of things like stationary phase and what. So he used this concept similar to that. It was actually a saddle point technique, but he used that, and from that he extracted the same picture that Sommerfeld came up with.
So that's the same thing, like a superluminal propagation kind of thing.
Is the same thing as what?
Superluminal propagation. no phase delay, that kind of thing. All right.
Superluminant.
Yeah, so like in waveguide, right? Like at the cutoff frequency, there is no phase change, right? Happens. So similar kind of thing, or what is in the stationary phase?
Stationary phase.
Yeah.
What is stationary phase?
That's
You talking?
evanescent waves comes in.
No. Evanescent waves can be explained in terms of stationary, but the stationary phase point becomes complex.
Mhm.
It's a little bit more complicated theory, but we don't go that way. There are other ways to explain it. But if you're talking about what is stationary phase,
Mhm.
I can tell you very easily. Okay, everybody here knows physical optics, right? So let's say that this was an infinite plane.
Mhm.
By the way, you need to buy my book. You'll find all the explanation. You have a wave coming in, okay? And there's a phase of that wave. Which way is it? Like it comes like the phase at this point relative to the phase. First it arrives here, then it arrives here. So it's a phase delay along, right? Let's assume there's no edge now. Now, the radiation interval says what? Every point on here illuminated will not create a
Cancels out.
wavelet.
Okay.
So from any point here to the observer, there's another phase. From the point e to the minus jkr over r. You get that? So you get e to the minus jkr as phase of the reflected part. We don't know how it's reflecting, but it's just mathematically going from, okay, from the surface to this.
That
And
omega
whatever the distance is, that is r, okay, to your,
Okay.
yeah. So let's say your fixed point here. You have every point on here is contributing. Like from every point, you're getting a contribution from that point to the observer.
Mhm.
Every point is contributing because the incident field is illuminating the whole structure.
Mhm.
But the incident field has a phase, which is a plane wave phase. It's delayed. It's delayed more and more and more as you go along.
Mhm.
Okay. Now, the radiation interval will take care of both the incident field and that forms the current over there, 2n cross h, which is the phase of the incident wave. And then the radiation interval has a phase e to the minus jkr over r, right? From every point, there's a spherical wave coming out.
Yeah.
Now you add this up, so that becomes an integral over the surface. Now, what happens is from all of these things, you're getting constructive, destructive interference.
Mhm.
But the only one path in which you get a constructive interference is where the phase of the incident wave is matched tangentially to the phase of the reflected wave.
Okay.
And that is the point of reflection, which according to Snell's law will give you incident angle and the reflected angle to be the same. So that's stationary phase. Everything else is destructively interfering. And so that's the concept of stationary phase. So the phase becomes the sum of the incident and the reflected phase becomes stationary at that point.
Mhm.
All the other points will destructively interfere.
Mhm.
That's stationary phase in a physical sense,
It's kind of PO method.
Huh? That's not PO method because PO method integrates brute force numerically over the whole structure.
Oh,
But that's a concept what they use to bring out that phase center of any aperture. Concept of stationary phase, they use to bring out the phase center of an aperture, antenna aperture.
Yeah.
When we are characterizing any antenna aperture in a chamber,
Yeah.
we need to find out its phase center.
That has to do with wavefronts.
Yeah.
Like where is the phase center of the antenna about which you're rotating?
Yeah.
But that can change with the observer. It's not a constant. It's usually constant. If it's a small antenna, it's usually constant over a large portion in the front.
Mm.
But it'll keep shifting after that, it will shift. But you're mostly interested in the main probe.
Yes.
And it'll be fairly stable,
Yeah.
But in general, it'll move around.
Yes.
with
That's
respect to frequency, it normally changes.
But that's not necessarily the same concept that these guys are trying to talk about.
Oh, okay.
Yeah. It's a little different. You're trying to say, I can have this weird wavefront. Where is the center of that wavefront? In a large portion of the forward radiation, it may be coming from a point. But then that point will move as you go further because it's no longer a spherical. It's spherical, but it has a pattern to it and it has phase to it. It's not a simple spherical. There's a modulation of the spherical wave. There's e to the minus j k r over r factor in the far field, right? Everybody knows about e to the minus j k r over r. That's the main. The center of that is where r is 0. That's your phase center. But the field pattern itself is complex. It has a phase.
Okay.
If it's constant phase, then it's roughly coming from the center where r is 0.
It is not a
But if it's not, then it'll move away from that. It's still a spherical wave mostly, but the phase is not constant over that initial sphere r equal to 0.
and the field is not 1 over r.
It is 1 over r.
Okay.
Just the amplitude.
Okay, this is a phase, right?
Yes, yeah. But the pattern is complex. It's a vector, it has direction, and it also got, so it's polarization. So polarization can change. That contributes to the pattern. The phase also of the pattern can change because different parts of the antenna interfere constructively or destructively.
Okay.
So then you get a pattern.
Mhm.
So that's the formation of the pattern. That's how both things work. But
In anywhere in the far field, the pattern will be stable or not stable. Like,
everywhere, what in the far field?
say for example, in far field we take a distance and then take the field. That will be same if you move little far away from it.
Oh yeah, you're talking about far field. Yeah. Of course, far field is characterized by the fact that the pattern remains the same no matter what the angular direction is. It stays the same in that direction, pattern-wise. Relative fields will remain the same. The pattern remains the same. In the far field, it doesn't change. It's like a mode. Waveguide mode stays the same in the waveguide. That way, the pattern remains the same in the far field. Yes, that's
But for this particular mode, that's the same thing.
particular one.
This stationary phase, right? That mode has also the same character.
Stationary phase is a little different concept. Your stationary phase tells you that
There's a question in the chat also.
Am I over like 1 hour already, right?
Yeah, we will make the presentation.
Okay, yeah.
Better we'll cover.
Yeah, I think we'll go through the presentation and then we'll take up the question.
Have it after that.
Oh, okay. So you want me to end up pretty soon?
No. So we want that you continue with the presentation and then we'll take up the questions at the end of.
Okay, so discussions.
Yeah.
This time.
Otherwise, things will.
Otherwise, taking.
We'll not converge.
No. I'll explain to you all your questions. Let me as much as I can. If I know the answer, I'll tell you. But yeah. Okay, it's a little different. Okay, but you're right. The antenna pattern does not change in the far field. That's the beauty of the far field. In the near field, it's not so.
Mhm.
And there's an extreme near field also. Anyway. So, okay, so wedge. Now, there's also a curved surface phenomena. People during the war were studying the effect of propagation of radio waves around the Earth. In the wartime, this was a very important problem. They wanted to communicate over long distances over the Earth. There's a source at height h1, observer at height h2, and you have some kind of propagation around the surface. And there was a guy in Russia called Fock, and he was actually an atomic physicist, but people that probably take quantum theory may have heard of him. Fock theory, or well, anyway, I won't go into it. Okay, so I'll go straight to electromagnetics. Right now, he came up with a mathematical expression for the field, and he said it creeps around the Earth. The way it creeps around, like a surface effect, surface wave, tracks along a curved surface. And I'm afraid that other people are staying in the back of my head, but hopefully once in a while I'll try to point towards so they can see my face once in a while. So, okay, so let me try to point this way. And so he came up with the theory. And in the US, there was another guy who was doing exactly the same thing Fock was doing. And they came up with something that was also discussed by Watson later in 1918. Earlier in 1918. Fock was in 1940s, okay, during the war. This thing went so quick. Okay. 1940s, okay. The wartime was during 40s. And 41, 42, 45. all that time period. And Pecker's also was doing that. But earlier, before that, Watson had found that you would have, you know, if you had a source here and an observer somewhere, you'd have waves going along here and along there. Creepy. And then supposing, let's say you were here, there'd be one path which is the shortest path, geodesic on the surface. There'd be a longer path, extremal, the longest path. So, but they're extremals, okay? They're geodesics on the path. Okay, so they're creeping waves. They're called creeping waves. So they came to be known. Now, just a quick historical fact. After the war, Fox's work was published. Pecker's, his work was classified. The US would not allow him to publish his work. Okay, so what happened? Of course, Fox's work was a little easier computationally to program and get results from. Analytical solution, but you still have to run numbers on it, right? It tells you, like, if you change the parameter here and there, what does the Fox function look like? So he was able to do all that, but it was still computationally, you had to compute it, right? So, okay, because his same solution, but slightly different functions, they could be related to each other. Okay, his work got classified. So at the end of the war, this guy was recognized. He got the Lenin Prize. Okay, of course he deserved it, but Picard didn't get anything. He got 0. All right, so that's what happens. So if you can't publish it, nobody will know about your work until much later. All right, so now what is happening? You suddenly see these are all not geometrical optics. Geometrical optics is really just incidence, reflection, and refraction. Then beyond what is not geometrical optics is diffraction. So anything in addition to geometrical optics is called diffraction. Okay, so remember that's the definition. And these are all separate problems: wedge, cylinder, the earth. You know, they're all like individual problems that show some kind of a ray theory is taking place here. You're seeing rays, you know, because you can go back to this and you can see that I can describe, if I say, according to Maxwell, from plane waves, you know that the direction of the plane wave is normal to the planar wavefront. So, and that's along the ray. So there's a ray that describes a plane wave propagation path. And then the phase front is normal to that ray. So what about a complex wavefront? Take a very large wavefront, take a small piece of that wavefront. What does it look like to you? It's a spherical wave, let's say, from an antenna. But if I take a small patch of it, what does it look like to you? Plane wave.
Plane wave, yeah.
So you can do plane wave tracking with rays for any complex wavefront. You break it up into very tiny pieces, and you find out that you can locally approximate a wavefront by plane waves. And then you can track the rays corresponding to. So now rays and wavefronts formally become normal congruencies from the idea of local plane wave propagation. That's in high frequencies. The wavefront has a huge surface, radius of curvature is large compared to wavelength. But take a small part of it, and that becomes a plane wave. And you can track that part like a plane wave. So that's the trick. When you think about this is known as principle of localization. It can be proved very nicely mathematically, but that's where the stationary phase also can come in. But anyhow, so without going through too much detail, I would say that people are starting to make. I can't seem to. There we go. Okay, so we're solving a lot of canonical problems here, right? This thing is going all over the place. So we have all these specific problems. What about a general problem with diffraction? So Lundberg and Klein came. They were at New York University, Courant Institute of Mathematical Sciences, and they wanted to say I want a high frequency solution, general solution to Maxwell's equations, given boundary conditions, I want to come up with a solution that's good for all high frequencies for any problem. So they expanded the wave equation right here at the bottom for the electric field. They expanded that in for the source free case, expanded it here. For source free case, divergence of each loop, you get that. K is the wave number. Omega is 2 pi f squared of mu naught epsilon. This is like for free space mu, non-magnetic medium, but epsilon could be any medium, and as long as it's non-magnetic, any dielectric. Then K0 is the wave number in free space. This is the wave number in the medium, which I'm assuming to be mu 0 and epsilon. Free space is mu naught E naught. Okay, I'm assuming non-magnetic now, but the electric field can be expanded in inverse powers of frequency. Omega is 2 pi f. F is the applied frequency of the wave, and this is raised to integer powers in n. It's a series in inverse powers of frequency. What does that do? As the frequency increases, the series will converge, right? As omega keeps increasing, more and more terms it should decrease. Actually, it doesn't do that. It decreases for a while and then it increases because it's an asymptotic series. You can show that asymptotic series are typically semi-convergent, and you need to truncate them when they start to go back up. And the errors will keep decreasing as your frequency increases. It takes more and more time for it to start getting bad. So, and in other words, you need only the first one or two terms. All right, what is the problem with these guys? Are great mathematicians, They showed the first term of this expansion with geometrical optics, incident, reflected, refractive ray fields. So they showed that Maxwell's equations gave rise to asymptotically expressions that gave rise to rays. A ray picture, it gave you geometrical optics as the first term. But then if you kept adding more and more terms, they wanted to see diffraction, they could never see it. They couldn't explain diffraction. Why? Very simple. I don't know why these guys didn't think of it. They're super mathematicians.
Boundary condition?
Huh?
Boundary condition?
No, boundary conditions give unique solution, but nothing more than that.
Okay.
So it wasn't that. But that's a good point. You should always satisfy boundary conditions, by the way. Otherwise, you don't have a unique answer. But no, what I wanted to show you was
But general solution without a boundary condition.
say that.
So general solution, they were trying to find out.
Yeah, but you don't know the general surface right now, so we're not applying boundary conditions. But in general, you could apply them to find the strengths of the fields that's gathered, right? But that means you're finding the coefficients according to your boundary. But what I wanted to point out was like in this solution here, in that solution, and in this solution here, you found that the diffraction that took place was fractional orders of inverse powers of wavelength, of frequency rather. It was not integer powers. It's not integer powers. It's like diffraction is 1 over omega to the 1/2 in edge diffraction. It's like for curved surfaces, it's something to another fractional power, so on. So this one wouldn't give it to you because even not even whole integer numbers of n would not give you diffraction. So at this point now things become more interesting, which would lead to a more important discussion later on. Is Lunenburg-Klein did not predict diffraction. Okay, that's the main thing. And
But there is no approximation here, right?
yeah, there is. This is an expansion. Remember, this little is not equal to, it's not asymptotically equal to. In this notation, mathematical notation, it's good for high frequencies. Okay, like omega very large. Omega is 2 pi f, f is large. Okay, so omega becomes large. So okay, we want to come to that. So that means that the n had to be fractional orders also. And this was shown very clearly by another guy who 100 years after Thomas Young's failed attempt at ray theory of diffraction came up with a beautiful theory of diffraction with rays. It was called the geometrical theory of diffraction. So then the GTD was born. And the man that came up with that beautiful idea was Keller. And he was also at the same place as Lundberg and Klein. He was Coronation of Mathematical Sciences. At that point in time, he was there. And he came up with the fact that if you solve the wedge diffraction problem in the time domain, he found that the difference between the Lundberg-Klein series and his solution was a circular wavefront coming from the edge, and which was absent in the Lundberg-Klein solution. And so he proved mathematically that Lundberg-Klein solution was no good for diffraction. It's good for certain things. Like if you want higher order terms and like to improve geometrical optics or physical optics, you can use the next term in the Lundberg-Klein series. But remember, in the Lundberg-Klein series, the first term is an amplitude correction of the geometrical optics. The second term is a phase correction. The third term is an amplitude correction. Typically, this is how things come out in electromagnetics. You look at the field of a point current in free space. What kind of terms would you get if I came close to the infinitesimal current, like current moment? What kind of terms would you see? In the far field, you'd see 1 over r type terms, right? 1 over r being the distance from the source. What would you see as you come closer and closer and closer?
All the higher
R square, 1 by r.
Higher order terms, r squared, 1 over r squared, 1 over r cubed, right?
Yeah.
Now look at those terms. 1 over r squared would be a phase correction. It would be a j in front of that. Then the next term would be an amplitude correction. This is how it typically goes on. So if you want to correct the phase, correct the amplitude, correct the phase, so on and so forth. Okay, but in the case of the point current, 1 over r cubed is the most you need to go. There's nothing beyond that. Okay, but what I'm trying to say is Keller came up with a theory that's generalized Fermat's principle. He said, now I introduce a new constraint. You can go from the source to the observer with a constraint that a point lie on the edge. That becomes edge diffraction. And that gives you the law of edge diffraction, which I'll come to in a minute. And then similar things, if you have a source and an observer and I have a curved surface, and if I take a string, it's a stretch string, it's a rubber string. I stretch it, and then what happens? I get an extremal path, which is a straight, if I'm in free space or something, just for discussion, straight line from the source to a tangent point on the surface. Then from that point, I creep along a geodesic on the surface. And then what happens is that rays are, he showed, continuously shed from the creeping wave along the forward tangents. So if I'm at some point behind the source here, and I'm going like this, I'm going from the source, creeping around, and then there's continuous diffraction as I go. So the field is attenuated in the shadow. If I'm here, one such ray that shed from me would reach the observer. Okay, so that part is a straight line, which is a geodesic. This part, which attaches is a straight line, detaches is a straight line. In between, there's a surface geodesic. Okay, so, but what he said was, then the path that connects the source to the observer with a constraint that part of it lie on the curved surface will give me creeping waves. So he mathematically, he was a mathematician. By the way, the best applied mathematician I ever know is Keller. You know, he passed away, by the way, not too long ago. But anyhow, okay. So he generalized it. Okay, and then he had some postulates.
That's the only solution, sir. That's the only solution to explain this.
Yeah. Well, ray-wise, yeah.
Okay.
Yeah. Because that's the Fermat's generalized Fermat's principle just gives you those ray paths. Now you got to find the field along there. How do you get that? Well, that's part of you have to solve canonical problems. Find an exact solution to a canonical problem you can solve exactly, that is, and then express that as an integral, evaluate the integral asymptotic of high frequencies, and then pops the GTD picture.
So it's a unique solution.
That's the beauty. Yeah, you get that. But so it takes a lot of work. So you have to be a good applied mathematician to solve canonical problems. And that's what I guess I've been doing most of my career, solving canonical problems to extend the, the toolbox so that people can use, coefficients for different kinds of diffraction effects. So you can model more general things. Okay. So that's what I've been mostly. I mean, that's not the only thing I do, but my interests have been in solving canonical problems, and so that's how you get diffraction coefficients, much like reflection and transmission coefficients. Let's say how much of the field got diffracted in a certain direction when the incident field hits your edge or curved surface or something. So that's the diffraction coefficient that Keller introduced. I won't go into too much of that, but I'll just tell you that basically for people interested in ray optics, I'll just say that think of a red ray here. At some point we'll cut off, and maybe at the end of this I'll cut off, and we can have lengthy discussions. And I go a long ways, but I think this is taking too much time now. Because all the other stuff took a long time. But this goes into the nitty-gritty of what kind of solutions exist. And I just go quickly and show you where I'm going to end up with this, so you know. But these are all the famous guys that have contributed to the ray theory.
Maybe you can share your slides
Yeah, they'll have the slides.
so they can read it later on.
They can read
Some
that.
question they
Yeah,
can drop
so,
in.
and then there's like, where does GTD have a problem?
Hmm.
Where does UTD come in, which is what Professor Quimjan and I developed UTD for edges. Then I continued that work for UTD for curved surfaces and so on, and combination of curved surfaces and edges.
But this
Like-
dielectric is not can be only taken by physical optics, like dielectric metal correct.
Well, you can do dielectrics. I've done some things with dielectrics, but there's a limit to what you can do, because if you can solve the canonical problem, you're okay. But canonical problems are very hard to solve with interior penetration and so on. But if it's slightly lossy, which most materials are, maybe you can do it, But you got to think about how to do this. I'm not saying GTD or ray theory is going to solve everything, but you got to be smart and augment it with other methods that work best for that case, So you shouldn't try to just use one hammer for everything, but use smart tools, combine them in some ways, to do things. So you can solve a lot of problems like that. So I won't go into that, but GTD or UTD needs some corrections at caustics and other things. And then I'll talk about PTD, the limitations of PTD. I'm sorry, I don't say anything about SPR because it's really a type of physical optics, if you ask me. Okay, I'll discuss that later. But then there are other methods that you need. I won't go into that, but this is the end of it. For materials, like you're talking about, dielectrics and so on. We've done some work. This guy in Russia, Tom Senior, and others, and myself have done some things on material coded structures. So, but I won't go into that. But I'll end up showing you. Oh, this is Keller, by the way, my advisor. And I was a student at the time when we came up with the edge diffraction theory, UTD. And then I extended it later to other things. But that was the time I got into it. And then other theories of diffraction came in, PTD, UFIMSEV, that's me, UTD, and this is for some very special cases where the field diffracted from one object hits another object. If there are like overlapping transition regions, then you need, in that very special case, you need what's known as spectral theory of diffraction. And that was colleague Ramatsamy and his advisor Raj Mitra that came up with that. So they call them 3 TDs, I think. I took a picture of this in Sweden sometime. He sent it to me. And they are some of the Italian collaborators of Quimjan. But I won't go in. I will quickly go over to what does the ray theory of diffraction do. So I'll come to this in just a second, but I want to tell you, oh, by the way, I showed this effect to some people. I can't do it here without a laser, but I can show you edge diffraction. with a laser pointer and a knife. So let me show you something here. First, let me go to Keller's theory and show you what he came up with. Why is it so great? That's because he generalized diffraction. And but then I'll go to results, okay? And then we'll close stuff. Right here. And this is how we fix Keller's theory. Okay, so I want to look at this. So I want to show you that Keller, through generalization of Fermat's principle, could solve a lot of problems using his diffracted rays. Because now with his generalization, any problem of diffraction could be visually seen in terms of diffracted rays. Like he said, at an edge, an incident ray that hits the edge tangent at this point of diffraction will create a cone of diffracted rays that come out from the edge. And the half cone angle is exactly equal to the angle the incident ray makes with the edge tangent at the point. This is like law of reflection, but so that this angle is equal to this angle. You know what I'm saying? What's happening? The incident wave is phase matched to the diffracted wave. Okay? It's like we have reflection. The incident phase is matched to the phase of the reflected wave to give you that extremal path. Right? Incident angle equals stationary point. Something like that. Actually, these are done by what's known as saddle point methods, which is another way of thinking of state. It's a stationary point, but not a stationary phase point. It's a different angle, but it's still a stationary point. Stationary phase is different from saddle point. The stationary point, stationary phase point is different from saddle point, but they're all stationary points. Critical points, they call them in the integral. So this is what happens at edges. This also happens at any line of discontinuity. It can also happen at a line of discontinuity in 3 dimensions where you have 2 different impedances or 2 different materials on either side. And then the incident ray will reflect differently from this side versus that side because the properties are different. Electrical properties are different. So reflection coefficients are different. So then the discontinuity in that must be compensated by diffraction. Okay? So you get diffracted rays coming from the junction of an electrical discontinuity. Not surface. The surface is smooth, but there's a discontinuity in materials. That creates diffraction. What about this? Incident ray hits, and there's the extension of the incident ray, okay, off the surface. It hits at this point, and this is the extension of that. And then you have, at this point, creeping waves launched, and then from every point on that creeping wave, you have rays shed along the forward tangent. So energy shed as you go into the shadow. So what's the difference? This is the lit side, where you can see the source of this incident ray. Down here, you don't see the source because it's blocked, and that's known as the shadow region. You also have shadow regions for edge diffraction, and so on and so forth. But diffraction will fill that space. Actually, when you have incident ray and reflected ray and all of that, it does cover up the space, but the reflected field fails as you come close to the shadow boundary because now surface effects take over, and you have to describe them correctly so that the Fock functions come into play here. Corner. Wave comes and hits a tip. It will diffract in all directions. Discontinuity in surface curvature. Flat surface joins smoothly to a curved surface. Remember, the radii of curvatures are discontinuous there. One is infinite radius, the other is finite. So you have an electrical discontinuity. Structural discontinuity. Here you have an electrical one, here you have a structural one. Again, there's diffraction there. So Keller says that the diffracted rays are produced at any electrical and or structural discontinuity. So geometrical discontinuity. All right, now let's go on to the examples and we'll close.
Section, right?
Examples. This one. So let's take a simple example, okay? The idea of the GTD is that it converts a complex problem into its simpler parts. And that's the beauty of it. So let's say you had a source here, and you had a teardrop type of structure, edge, curved surface, and right now I make this impenetrable, not a dielectric, but so on. Now, what happens is that if I'm observing the field here, I have a direct ray, I have a reflected ray, according to a reflection coefficient, but I can also have a diffracted field, which says how much of the diffracted field went in this direction through a diffraction coefficient that characterizes that. Let's say I find this diffraction coefficient from canonical problems, and I know with, again, principle of localization, how I can extend the canonical problem of flat face wedges to a curved edge. I can do that very easily. And once I get that, I put that in my catalog. I don't have to rederive it again and again.
Okay.
And then I use it. Now look at what happens. First of all, there's a reflection shadow boundary which is tangent. So the field that hits this reflects according to the tangent plane approximation at that point. So it goes according to a Snell's law. And then there's no reflected field after that because the surface stops. There's no surface to reflect from, right? So you have a truncation of the reflected field. So you create a reflection shadow boundary. What that means is beyond this, there's no reflected field. Then if this is the incident field, it creates an incident shadow boundary because below that you don't see the source directly. So this is the shadow. So you have another boundary. Now Keller's theory had one little problem, and actually a big problem, and that was that his fields became singular here and here, infinite. And if the frequency was made lower and lower, still a high frequency, but if you brought it down, the region around which the singularity took place became bigger and bigger angularly. So the results got worse and worse over a bigger region. So the engineers, as we all know, will take your software and try to apply it to problems where maybe it's strictly not valid. But they don't know that because they don't have the EM background to figure that out. What kind of limitations does the software have? Now, that's precisely what happened here. There's transition regions around the shadow boundaries. I call them transition regions. They got bigger and bigger, and they got horrible patterns, discontinuities, infinities, all kinds of things going on. And if you had a sponsor that was giving you money to find patterns of antennas and structures or whatever it might be, or scattering from structures, and he saw patterns like that, he'd immediately pull your funding off, right? So you had to fix it. And that's where we came in at Ohio State. When I first joined, we started to work on that edge diffraction problem with my advisor. That was actually my master's thesis. And we came up with the edge diffraction solution. And we made Keller's theory uniform. So it became uniform geometrical theory of diffraction, UTD. We call it uniform theory of diffraction.
So, sir, if we put this in a bigger surface, then compute the overall energy flow through the surface. This Keller's theory will give us infinities.
No, because when you integrate, you have to integrate that, right?
Yeah.
Integration is always a smoothing process. You'll never get singularities.
Okay.
Yeah. That's the nice thing about integrals. But then integral has to be done over the whole surface. If I make the frequency higher and higher and higher, at some point, you'll have computational issues. So, but here, we don't go through currents. We don't solve for currents. We go through rays. We bypass currents completely. So that's the advantage of ray methods. And then they give you the physics, ray physics. So the question now is, what happens at these boundaries? So we fixed Keller's theory over here and here, ray diffraction. And then I worked later on other people had done work like Falk and others, but they didn't really solve canonical problems like I did and put them in the UTD form where I could recognize the UTD results, which worked in the transition region. And outside that, it went to Keller's postulates. Keller didn't solve all these problems canonically. He solved one or two of them. But based on that, he came up with this geometrical theory. It was a beautiful theory. It was the most important theory after World War II, along with another theory Does anybody know what the theory might be?
String theory?
Huh?
In physics or in electromagnetics?
No, in electromagnetics.
Moments, sir. Method of moments. Method of moments?
Yes, method of moments was the other one. And that again was put on a firm footing by Harrington.
Yeah.
He was the one that showed how to start doing practical problems with subsectional basis functions. Now, I know the time's running out, but I have to tell you a little story about that. First of all, let me tell you that Harrington, I knew Harrington quite well. He still is around, but I think he's still around in Chicago. But I used to know him quite well. And that's because he and my advisor did their PhD together in the same place. I come from Ohio State, and my advisor, Quimjan, was a professor there. And he also graduated from Ohio State. And he and Harrington worked together. And the advisor for my advisor and for Harrington was Professor Rumsey.
Oh, I mean, the physics professor?
Yeah, Ramsey, you gave that.
Rumsey, there's an interesting story about that too. He had a bachelor's, that's all he had. He had a bachelor's, but tripos and mathematics from Oxford.
Okay.
So he was like, he was probably one of the really hotshot mathematicians, applied mathematicians, but good sense of physics, And he came to our lab as a director. At that time, I was not even there. I came much later, but I did meet Rumsey, by the way, because he was my advisor's advisor. So of course, I had the pleasure of meeting Victor Rumsey, Vic Rumsey, used to call him. So he was the first director of our lab, actually. And okay, so he was the advisor for Harrington and Quimjan. And the Rumsey's reaction concept was really putting reciprocity in a different form so that you could talk about observables in electromagnetics, much like you talk about observables in quantum mechanics. Like what are the observables? Impedance, what else? There are a lot of radar cross section. And these are all observables. You can write them in terms of reactions. Any generalized reciprocity, like the original problem, the reciprocal problems don't have to be the same. And actually, find in my book, you'll find examples of reciprocity you'll never find anywhere else. Okay, but they're engineering applications. And the only thing is you got to have the same volume of space, but otherwise they're different problems. And you can combine two different problems through reactions, how they react with each other. And come up with beautiful, actually, that's the formulation of EFI, MFI. You can get all that from reaction theory.
Yeah.
But people don't look at it that way because that gives you so much physics if you look at it from that point of view. People just go write equations out.
So there is a directionality in it?
Huh?
There is a directionality in it, in the system?
Directionality.
In the sense, the reciprocity is different from the classical sense you mentioned, right?
Can you hear us?
I mean,
You're talking softly.
sorry.
You have to.
So what I'm thinking is reciprocity is different in this concept, right?
No, reciprocity is reciprocity. If you got a reciprocal system, it just says interchange of source and observer.
Yeah. Okay.
Shapes the response. But if you generalize it, it's different.
Okay.
But then it works for more general cases. And there are situations where it doesn't. But if you have nonlinear materials and stuff, then you have. But there's another form of, it's not reciprocity, but there's a relation between the direct and
Simple way, I have a transmitter, I have a receiver.
Yeah.
Whether S11 and S22 may be different, but S21, the transmission from one to another, either from here or here.
yeah, S12 equals S21 for a reciprocal problem.
Hmm.
But not all problems are reciprocal, majority of them.
Yeah.
But that doesn't mean there's no relation between the two.
Mm-hmm.
Okay. So, but remember, it's not power. It's E cross H without the conjugate. Those are reactions. Okay.
Okay. So it's not real power basically.
No, there's
It's
no power here, but I think that method of moments,
interaction between two fields.
method of moments is basically the reaction concept only.
Reciprocity is actually based on reactions, but it didn't come out like that in the beginning. But then Rumsey put it in the form of reactions. But he generalized reciprocity. I call that generalized reciprocity.
Mhm.
But they're nothing but reactions. Measurement is a reaction. Everybody makes measurements of antennas, right? Impedance and other patterns and so on. What are you measuring? You're measuring reactions. You're measuring,
Coupling basically, right?
yeah, you're measuring the voltage. The voltage is it's your meters, whatever. It's recording the fields. What it is, it's a reaction between the field that you're measuring, and the measuring probe would also be
But
radiating. Here it's receiving, but when it's radiating, it has a field. And the reaction between the radiating field of that receiver, which now acts as a transmitter, and the field that you're measuring, that reaction is what you measure. People don't tell you that, but that's what you're doing. You're measuring a reaction.
it's a whole system basically, right?
Yeah, but it's so there are reciprocal problems that are interacting, and that's what you're measuring. So he gives you a physical idea of what a measurement is, but measurement is the reaction. When you go to the lab, make an antenna pattern measurement, it's a reaction. So, okay. Buy my book. It's in there. You'll never find, I hate to say this, but you might think I'm too my own trouble. But believe me, I've done this because I'm trying to explain things to people, and I hope they enjoy reading it and get inspired by it. So that was my idea of writing the book. I put all the knowledge I have, most of it, in the book. So,
Sir, I have one more question.
yes.
So where is Schwinger coming into the picture?
When is one?
Schwinger, the Nobel Prize winner, right? He did a lot of work.
Julian Schwinger.
Yeah.
Schwinger's work comes in terms of how obstacles and waveguides
Okay.
did things, and he came up with the Wiener-Hoff method in a way, to explain some of those things. But he didn't directly do anything. Well, of course, he comes into quantum electrodynamics.
Yeah.
He and Feynman and Tomanoga, I think, in Japan,
Yeah.
they shared the Nobel Prize for quantum electrodynamics.
Yeah.
But that's all I know. I don't. Okay, coming back to them, let's quickly end up this. So you have now another shadow boundary here, which I call the surface shadow boundary. Why? If you're here, you have a direct ray and a reflected ray from this point, right? Okay. Now, what happens is that if I start taking the observer down further and further close to this line here, what happens? On this side of the shadow boundary, I see the reflected field. On the other side, I don't, because it's shadow. Now, what happens is that this space is filled by creeping waves from which rays come out along the forward tangent. They call the surface diffracted rays. So they fill up the space. Also, the reflected geometrical optics field will start giving you error. In fact, it'll go to zero along this boundary as you come here. It's wrong, but it gives you zero. But that's because the surface effects are important. So things have to start changing across here and go continuously. Now, Keller's theory will give you jumps here, here, here. Keller's theory is no good with shadow boundaries. So, one quick historical fact. This is not a criticism of Keller's theory. Keller was the finest mathematician that I know, applied math person that I know. Now, he knew what was going on, okay? But he was not interested in that, fixing it, because he worked at, he said, asymptotically high frequency, right? Excuse me. What he thought was, at very high frequencies, the transition region collapses. So the region where Keller's theory goes bad is now becoming narrower and narrower. And he doesn't care what happens here. Easily you can just, but it doesn't quite work like that. Guess what? It's not so good there, even with that. And for practical frequencies, you'll see big jumps, and a lot of problems. So you have to go to infinite frequencies to get to where Keller's theory works. Now, Keller knew what to do to fix it, but he didn't have time to fix it. So he gave us a chance to fix it. So we became the practical guys, and we knew, but it takes mathematics to fix it. And every fix up depends on the diffraction process. And to every diffraction process, there's a corresponding, I call it transition function, which goes through these regions, transition regions. And the surface diffraction is characterized by Fock functions, edge diffraction by Fresnel functions, caustic, the caustic infinities fixed by Airy functions, the cusps of caustics fixed by parabolic cylinder functions. So you have to massage your integrals in terms of some of these, knowing what the physics is going to be. So it works hand in hand, but it pops out of the mathematics also. But the nice thing is, when you do the asymptotics, the ray picture pops out in front of your face. And then from there you say, that's a diffraction coefficient. So everything else satisfies the ray optics. Correct. Outside the diffracting obstacle, everything is ray optics. Well, the laws of ray optics hold. So it's a very simple idea. Very simple algebraic expressions for the ray fields. But you have to know the diffraction coefficients. How do you find them? From canonical forms. We'll talk more about it in the afternoon. And then there are failures of GTD or UTD. All right, let me finish about Keller's theory. What was he doing then instead? He didn't want to fix these problems for engineers. Okay, so we had to do I won't say dirty, but we had to do the work. And we were happy to do it because, we want to apply the theory. But it took mathematics to do it. Once you got the end result, it was easy to code up. It was simple. Like big functions typically, things. So that's why it's very beautiful. But Keller was interested in proving uniqueness and existence and uniqueness of the solution. And that's what mathematicians always do. Does your solution exist? And if your solution exists, is it unique? That's what he was trying to prove. And so what then happens is he tried for many years to do this and he failed. He was not able to show uniqueness. So I can come up with this solution to a diffraction problem. You can come up with another solution. We can all have different solutions. They're not unique, right? But the numerical results from us, if we have good solutions, will be almost the same. But they're not unique. Okay. So Professor Andy Lee can have with his colleague or his co-author was the director of the Illinois EM lab, Deschamps. They came up with UAT, Uniform Asymptotic Theory, which is exactly the same kind of theory that Russians came up with, Borovikov and Kinberg came up with. Or we could go to Kumjan and Pathak theory, of UTD, based on my thesis, but we have different solutions, but we come up with the same answers pretty much, So that's okay. So we take a complex object and then you can also have interaction, creeping wave, diffracting, or something like this, diffracting from the edge and launching a creeping wave. The interaction. But typically you don't need but 2 interactions at the most. Okay. If you're dealing with too many interactions, you're trying to push it to the lower frequency, almost down to the resonance region, or I would say you're straining the method. Because asymptotics, if you add more interactions, you're adding higher and higher order terms. And what happens is they initially converge, but then they start to diverge. So you have to know where to cut it off. So I would say never go beyond 1 or 2 interactions, And what do you say? How do I know as an engineer if one interaction is sufficient, or if it is not, I have to add the other? When do I do that? Very simple. If you ignore a ray, then what happens is that the ray cuts off. There's a higher order effect that has to be included. The second diffraction is to take place, or reflection is to take place. So you'll see a small jump in your patterns. Then you know you've ignored a second order interaction. Then you add it in. So the physics makes it very easy, to fix things. That's the beauty of this method. Okay, so you take a complex object. If you know the diffraction functions, once and for all, go to your catalog and use it. Okay, let's go to the results now. Here's an airplane. Okay, you got an antenna behind the airplane. So what do? You find out the ray that goes from the antenna to tip of the wing. It can go to vertical stabilizer, cone of diffraction. By the way, I can show this cone of diffraction using a laser knife, but we don't have that here. And then you can have a creeping wave that hits this and refracts in a cone from this edge. So you see things like that. Depending on where you're looking at, the dominant rays will contribute. Okay. Now, edge diffraction is most important. Next, surface diffraction, then corner diffraction, and so on in the hierarchy of rays. Okay. So let's go to some results and so how accurate is this method? Well, here's this paper that I wrote one time on elemental antennas on a general curved surface. So it has to be convex. So here's a little monopole. And I'm looking at the plane tangent to this monopole on the surface, which is a spheroidal surface. It's a metallic surface. We measured the results in the shadow boundary plane. Which shadow boundary plane is the plane tangent to the antenna. Plane tangent to the surface at the antenna. So that's the shadow boundary plane. It's a flat surface, mathematical surface. And then you're going in that plane and you're going around it. You're making a pattern measurement. Okay. Now, what do you see if you have a monopole? And if there's no curved surface, there's a flat surface, metallic surface. What would you see? How many polarizations would you see for a monopole? Electric monopole. Only the vertical, right?
Vertical.
Vertical. It will be going constant. That's typically what you see, is the copole. But the surface is curved here. What happens? The curvature does something funny. It creates this cross pole, which you don't see in a flat surface. And this is a very good prediction of, this is a very difficult measurement, even in the 80s when we made it. By the way, the compact range was first developed here, also Ohio State, by a guy called Burnside, who made these measurements, by the way. I did the theory, one of my co-authors, Nan Wong, did the computations, because you have to compute geodesic paths on this. For Ansys, that's the important thing. If you can compute geodesics on a curved surface, then UTD becomes very easy to use. But nobody has done that. We tried to do this, but we all retired about that time and the students left. And so we did this work for Applied EM, which was part of CJ Reddy's outfit. Then it got bought by Altair. Came out there actually. It was FICO. We tried to put that in FICO, but then it became part of it. So we tried to use patches to find the geodesics. These triangular patches had edges. Those are flat facets, right? Then we could use edge diffraction theory to track the geodesic on a curved surface as an approximation. You know, if you have two facets, rays coming like this, it'll diffract on the cone of diffraction or about the edge. You find the diffracted ray. And then it'll go and, you know, you can keep doing this to track. It'll give you a geodesic. But what happens is that you get phase errors because it's not a curved surface. It's a faceted approximation, piecewise linear type of thing. So you have to project that on to the surface and try to fix it. That thing got fixed. We got a beta version, which is in the FICO code now. But we never refined it enough to where we would like to see it, you know, used. So I'm trying to look for places to do geodesic computations, you know. Somebody good in computer science, mathematics would be able to do this very easily, and then put it in graphics or something. But that would be ideal. So if you guys had geodesic paths, you'd be able to do this kind of stuff. And that's the limitation of SPR, by the way. I have to talk to you about that. Again, I wouldn't say SPR is, I'm not saying SPR is no good. It is good for certain things. And I should say, again, I know the person that developed it, Professor Lee. I know him well, I respect him. But his method works for certain things and not everything. And now I've incorporated UTD, my stuff, for curved surfaces. I think Del Cross is a company that does that.
Exactly.
So they put that in there. But already the SPR is a unwieldy code to that adding bells and whistles now. And it's becoming more and more cumbersome, I hear. So, but that's what you have right now, so you can use it. But if you can track geodesics, you know, you have a big jump. Then UTD, I think the reason why UTD is not as popular as PO and PTD is because geodesics have to be computed. Edge diffraction is fine, but surface diffraction is the
So for the concave surface, is there any limitation for finding the geodesic?
concave surfaces. You can use multiple bounces
Okay.
to start with, but cutoff Don't use too many bounces because the asymptotic series is getting to be bad. So you have to know when to stop it. You have to be an engineer to cut it off. But there are whispering gallery modes you can convert. The guy that does that is Felsen. I haven't gone through all that, but it's in there. You can look at those. Okay, let me quickly go through these and so I can quit. So what causes this? What's the physics of that? That's torsion. I don't have can I get a piece of paper here? Can I put a straight line on the back of this? Let me see if I have a pen and do that. Can I borrow your notebook? To draw a painting. Fine.
You want this marker to go?
No, this is good. Okay, fine. But I don't want to spoil the notebook. It's okay. I think this. Okay, let me show you what I mean. On a flat surface, the straight lines. So cylinder can be mapped to a straight surface, but look at this, it's a helix. So on a cylinder, it's a helix. A cone, no. On a cone, you'll find it goes like to a minimum distance from the tip and starts coming down again. So on a general surface, it'll do a different. Now, what's happening? The ray is twisting. The twist is defined in differential geometry as torsion. And we have torsion here. So I can tell you how the polarization of the rays change. Geodesics. Very nice simple vector formulation that says, no engineer will tell you based on numerical methods how the polarization, like an engineer, hey, what would it give me in some direction here on the general surface? But this method will give it to you. No? So that's the nice thing about ray methods. All right, so this is caused by torsion. The twist, polarization comes into play. And it tells you exactly how it comes. So the physics is the most important thing. You engineers have to have physics. If you don't have physics, you can't figure out what you're getting, So that's very important. Here's an antenna on a cone. It's a slot antenna. I'm looking at the pattern in the plane containing the slot and the generator on the cone, which is the axis of the axis of the cone and the generator. The generator that passes through the slot, I should say. The generator is that line, an angle along the cone surface passing through the slot. And then the axis of the cone is the dashed line. And if I look at the pattern of this radial slot in that plane, I'm comparing with eigenfunction solution of Hughes. Nice relation. But how many rays am I using? Well, I'm using those geodesic paths that I showed you. Now here's another one. I'm looking at like 80 degrees from the vertical. In this case, I'm in that plane, okay? Whatever that plane, elevation plane is. Here I'm looking at, if I look at 80 degrees from the cone axis and go around in the cone, and I have a radial slot here, here's the pattern, the two E phi and the E theta. And again, I'm comparing with the exact solution, okay? Some differences here because there's a tip scattering. I use an approximation that I actually take from Professor Andy Lee's work. He had come up with a numerical approximation to a cone tip diffraction. I use this solution for that, but it's a minor contribution. Most of it really comes from just the geodesics. Okay, so let's go to the next page. But this shows how it works. Here's a cone with two slots, and I'm looking at the slot coupling A to B, slot 1 to slot 2 coupling. With a fixed distance between the slots, but I'm changing the frequency. And as I do that, I get these results. I'm comparing again with exact solution and experiment. Now, what's causing the ripple there? If you got this from a numerical solution and say, okay, here's the answer. I have the answer.
Because it can travel in both directions. And then through the cone. Right?
But remember now, there's a fixed. So it goes, and then there's a change. But more than that, two things are happening. One is you're getting the shortest part, and then you're also getting the other part.
Constantly instead.
Yeah, this between those two. So that's what you're getting here. Then now this is staggered slot, so one shifted from the other. Okay, next. All right, now we go to my friend Burnside, who passed away a few years ago, not too long ago. He modeled an F-16 here, and we're seeing the patterns, E theta and E phi, cross pole, copole, nose, left wing, right wing, and all. So these are at an angle of 80 degrees from the vertical conical skin, and there's a monopole behind the cockpit. Monopole antenna. I think it's a TACAN antenna or something. So you have this on the space shuttle again, conical scan. You have these results, but look at the measurements and theory. The measurements were done at the naval. What is it? Point Nobu? There's a naval laboratory that did all the measurements, scale model measurements. And we found this agreement. So we've also done private aircraft. We've done missiles. We have done drones. We've done all kinds of things like that. So you can model. Now you may ask me, how do I model wings and things like that? For antennas, you don't need to be very precise about that model because it is based primarily on the shadowing. If I have an antenna here, does the precise shape of this edge matter? No, it's the projection, the shadowing effect that's more important. So if you get the silhouette of that, works fine. That's all you need. So we can model very complex things with spheroids and plates. But now with Dr. Reddy's codes, which we tried to develop, we didn't completely get to the point where we want, but it's a good start. We can do faceted models, which will then smooth up from as the geodesic calculation. But I said the geodesic can be computed by using faceted models and then smoothing them out to get the correct phase. So that's
It's correction, the correction of that facets into smooth.
right. You map it out to the actual surface to make the phase correction. So again, you don't have to go very far. Why? Because the rays are shed tangentially along the surface ray path, and so energy is lost exponentially. And so you go only a small distance, you're fine. But during that time, you need to, include the fields because on those paths you need to get accuracy. So, okay, you might think that I can only do exterior grounds. Not true. Actually, Felsen is a whole class of interior grounds like the ray methods, GTD. And we showed that I can now, with a combination of what's known as equivalent current theory, I can take out the waveguide after I come in with the and more. I have a circular waveguide with the open end here. I cut it off. I find the reflection into all other modes because I'm working at a frequency where I can excite the first two modes. And so I get a reflection coefficient of the same dominant mode and then into the next mode. Incident mode is dominant. The reflected mode is the second order mode. And I'm getting two results, one for this, one for the higher order mode, one for this. There's a magnitude and phase. And I'm comparing this with an exact solution by Einstein, the Russian guy. He's published it in a book called Function Theoretic Methods. It's a Russian publication. But I can do these kind of problems. So I've done radar cross section of inlets with ray methods. And so as Professor Lee using shooting and bouncing, we use a different method. We call it generalized ray expansion. And we can do terminations, modulation of the blades on the radar return. So we can do all. So a large class of problems. I can't say we can do everything by ray methods, but we can do all large things. And even if you don't have diffraction coefficients, the ray should give you some idea of what to expect in your numerical solutions. You see some peaks and patterns and stuff. You can interpret those. Hey, it's coming from here, it's coming from there, So it gives you some physics. Like with my students, they made measurements. I could tell where things were coming from because of the beautiful physics. Okay,
So one idea is one.
Is it possible to apply ray methods at quantum level and in photonics, especially as we approach the limit of Moore's law?
Ray methods, I don't know how you'd apply them at the quantum level because you're talking about interaction of particles and waves. So I would say at that point, photons are the way to describe things. I would say I don't know. I don't have the answer to that. I'm not into microscopic stuff. I'm more into macroscopic scales, so I cannot answer that. But I don't think it's so easy to do that.
Another question is it possible to use Ray method for analyzing interaction of beams having orbital angular momentums?
I would say at this point, I don't know. It's possible, I would think, but I don't know at this
So
point.
we did some POC for that with our SPR tool, where we have a OM array on
Yeah.
one side and on the other side is another OM.
Yeah.
Multiple modes we transmit at same time and right.
Yeah, you're talking about optical modes now and beam modes, right?
It's a OAM method which is now coming in the 6G technology.
What is OM?
It's orbital angular moments.
Orbital length.
Orbital angular moments, yeah.
Okay.
It's kind of another type of multiplexing.
But that is at
Data multiplexing. So you can send the same space, you can send same frequency, either horizontal, vertical,
that is the
polarization.
that is basically Nija's concept of spin actually. Spin has got infinite states, sir, in quantum theory.
Oh.
Since spin has an infinite states, infinite number of states are possible. So they're utilizing those states to have
Spin will only up and down.
yeah. No,
In
states.
Two
Like
states.
it goes like this.
Oh, like a circular pole.
Yeah.
So you may have a 3-4 antennas. While sending, you will be having some phase delay in circular way. So that one mode will have this kind of a rotation, angular rotation. Then I can have same space with another 4 antenna with opposite spin.
Okay.
So that these waves will go through the same place without interacting.
Without interacting.
Oh, yeah, they're orthogonal.
Orthogonal.
Yeah.
So like that, you can apply different phase so that you can send multiple modes
Uh-huh.
to the same space without interactions, and you can decode it. That's it.
Yeah. Well, I mean, it may be possible, but I'll have to look at it. I'm not
tried.
familiar with OM,
Yeah.
but because I'm not a computational person per se, I'm more into theoretical. Yeah, but I haven't looked at this, but it'd be interesting to find out. I would like to know about it. I'm not sure I know enough about it.
Some of the study we can share.
But I'm into beam methods, by the way. I can, if you want to do high power electromagnetics, maybe beam weapons or beam other reasons to use beams. We can do that. I've used beams for efficient near field to far field transformations. I've used beams to do things faster than the FMM for taking the interaction not between the nearest neighbors, but between the next to nearest neighbors. And this was done because we could expand the fields on each of those, partitions that we had into beams going in different. So the beams that would interact most strongly were the ones in opposite direction to each other. Not
But can we use your ray tracing to design a reconfigurable polarized antenna? Because if
reconfigurable.
because you are saying as in the cone, you're saying that beam is going like that and polarization is changing.
Yeah.
So if we trace the path and we know like what polarization is there on what point, we can put the antenna over there and we can get different polarization on the same surface.
Yeah, we could do. So how do you want to use it, huh?
Because nowadays we are trying to have some kind of a receiver which is having multiple polarizations, so that whatever signals are coming, we are not losing it in the communication satellite. So if the
If you can model any,
if you can model using your ray tracing, the different points.
include that information. If you can do array modeling, yeah, it should be. But I'm more interested in beam methods. I can do near field, far field transform. I can now. I don't know, but I'm not a computational expert. But we have the same. We can show that in this paper that we wrote on beam to beam interactions. Like we do a numerical study, and we take near neighbors and then far out neighbors. We have these, regions, spherical regions around the collection of Epigon and FMM. They collect a bunch of basis functions into something. And then they have they split up the scattering object into a bunch of these regions, right? And then these regions speak to each other.
Mhm.
And they use spherical harmonics, I think, to connect them. Now we use beams. We throw beams from the center of each of these spheres, and the beams that face each other are the most strongly interacting ones. So we don't worry about all the other ones. We throw them out because they're below a certain threshold. We don't need them. So we have a way to compute things very fast, and the operational count is exactly the same as the FMM. And that we have shown this in the paper. We have published it. and now Professor Raj Mitra and I talked about this method. He was interested. And so I asked him, what are your thoughts on whether this is comparable to the FMM or not? He said it actually should be better because although the operational count is the same, there's a computational cost associated with getting it in the form of the FMM or whatever it is. And in my case, it'd be much lower, he said. So that was his expert thinking. So I don't know. But mine is a very simple way to think about it. So you don't have to do spherical harmonics and all that jugglery of mathematics, come up with it, That's of course an exact way of doing it, but I have something that's pretty close to being exact, but it's very accurate. It does. So beams can be used for a number of things. You told me about this angular momentum thing. I'll have to think about that, but I'm sure there are uses for it, but I haven't looked into it. It's just whatever interests me, I work on, but I haven't looked. But I'll be interested about it.
Yeah, some nice material.
Yeah, sure. My more interesting thing at this point is to get people to do geodesics on the curved surface, because that is what is holding it back. If you can do that, you can do a whole class of new problems very easily. Okay, with that I close. I'm sorry for being over a couple of hours, but I like to talk, and that's.
Yeah, we actually went all the way to almost 3 hours of here.
Yeah, so it's not possible to do it with questions.
I think we can close this meeting and we can go for our lines.
Okay, and we'll come back. Yeah, I'd be happy to answer any number. I'm free, so
Yeah.
you can whatever I can answer.
I
Otherwise,
didn't see anything.
if I don't know something, I'll say I don't know.
Any questions they have online, you can just see if somebody wants to ask. I think if someone wants to ask anything, they can.
So, do you see machine learning can help on this kind of problems? This machine learning, right?
Machine
Machine
Machine learning or artificial
learning,
AI, ML, yeah.
Well,
AI stuff. Yeah, there's some things you can probably do. Repeated calculations, given the data, you can.
Maybe your geodesics can be
Yeah,
computed using ML.
But
Based on whatever the library you've created. If you feed that library,
but it has to be able to compute. How would you compute geodesics? Is the question. Are you going to solve a geodesic differential equation? Like you have, there's the differential equation for geodesics.
yes.
And you can solve for it. You have to know the surface properties, the Christoffel symbols for that, and all of that. Are you going to use facets to do it? I'm not quite sure.
We have to generate a kind of a lookup table based on already computed geodesics.
Yeah, but then if you go to something, it'll try to put cone and cylinders,
Yeah.
something very general, you get garbage,
It is same like whatever they do in measure movements. So they have got some RWS, Rao Wilson Gleason, RWG basis function. They try to fit into any arbitrary shape. And then whatever some funny shapes they have, then they cut off and they go for some correction.
Nice to track. It would be nice to track. The problem is, given a source position and observer position, how do you track this,
Correct.
That's the big problem. But it's not, it cannot be done. We have done it. I mean, we have actually.
Yeah, that's what.
The best thing is to start with a source on the body, like an antenna on the surface, and then track one way. Keep one fixed, and then move your observer around and get different paths. Or just shoot your rays like Andy Lee does in the shooting and bouncing. Let them go wherever according to the geodesics.
But I'm sure if some AML expert sits with you, I think we can work it out.
Yeah, well, I don't know how to use AI here.
No, that's what somebody has to be there who is good in
Yeah,
that.
because if you put something in,
Even I'm also not good in that, so I don't know.
yeah, like take a patch antenna. Hundreds of people have written papers on patch.
Yeah, that's right.
So they can put that into AI and do a new patch antenna.
But we don't know. Sometimes AI gives some solution which does not obey physics.
Well, that's what I'm saying. So, but if you get something that doesn't have the right physics, and if you put in a lot of things that AI is taking in from extrapolating from different places and trying to do something intelligent. Actually, they come out with garbage. So
Yeah, that's a risk.
I'm the old-fashioned guy. I go to the basic mathematics and figure out, what approximation works the best.
But I'm sure that whatever data you've generated over the papers, if you fusion that data in a database,
Well, look, you
You
can
can
have
come up-
points, okay, you
Yeah.
can have points on the survey, you can
Yes.
define them.
Yeah.
Then how would you mesh it up? Like people already have meshes.
yes.
Then how can you track geodesics on that, given a point on the surface? So this should be possible. I don't know if AI is required for that, but you should be able to do something. Maybe you can use it because a large number of data points, so AI could be used.
Yes. Some kind of interpolation.
Yeah, but the problem is you can get multiple geodesics. They can converge to a caustic also.
Hmm.
But that's okay. At the first go around, ignore those caustics.
Yes.
It's okay.
So, sir, this geodesic is a tensor actually.
Tensor.
Is it?
Geodesic is not a tensor. It's a physical path, but it's expressed in terms of tensor calculus because the geodesic equation satisfies
Hmm.
differential equation that requires some gamma, I guess, that we call, I don't know, Christopher symbols.
Christopher.
I don't know.
But G mu kind
It's
of.
been a long time since I've done that. So
We'll break for lunch.
Yes.
yeah, sure. Thank you.
Close the
Sorry. Thank you for patience. Your patience. But I hope I gave you some insights.
It was very informative session. So
Thank you.
we learned a lot.
After the university, I think
Yeah.
after a long time, I think this is
Thanks everyone for joining this call. We are going to conclude, and who are not able to join, they will share the recording with everyone, so you can have this. Professor, I'm just checking. Is it possible to share the PDF also all the people? Sorry, is it possible to share the PDF?
Please go ahead.
Okay.
And then you can read on your own what I've not covered because it should be easy to understand.
Sure. Yeah, we are concluding now. Thanks for everyone. Taking copy of this.
I have another presentation that I had. It doesn't go through history, but it goes through the different methods, PTD, GTD, UTD, and whatnot.